In this video, we are going to be talking about inequalities and also about interval notation. So, if you're remembering back a couple of sections previously, we talked about equations, and those were just statements that involved an equal sign. If instead of having an equal sign, you have one of these, less than, greater than, less than or equal to, greater than or equal to, then what you've got, instead of being an equation, you've got an inequality. And so inequalities can be used to describe intervals of real numbers. So for example, you could describe all the values of x that are less than 3/2, for example, or you could describe all the values of x that are between +2 and -2. That's one way in which inequalities can show up. But there are some cases where we might have an inequality and we'll also need to solve for what are the values of x that would satisfy that inequality. So there's a few things that we'll be going through in this video. Now, to start with, for interval notation, another way to describe that same idea of an interval of real numbers, we describe it by using the endpoints of the interval and using either round brackets or square brackets, depending on whether we're not including or including those endpoints. So the idea here is that we'll put a round bracket if we're not including that endpoint, and we'll include a square bracket if the endpoint is being included. There's one little other exception here, which is round brackets are also used if one of the endpoints is unbounded, if we're going to positive infinity or negative infinity. And the reason for that is, of course, because infinity is not a number. It's a concept of limitlessness. And so it's not a number, so it can't be included. We can only include numbers. That would be the only time in which we would use square brackets. So some examples of me writing things in interval notation. So here for a, these are all the values of x that are between 2 and 5, including the 2 and including the 5. So this would be the interval from 2 up to 5, including the 2, including the 5. Notice that for interval notation, we always write the interval in order from smaller value to larger value. So it's going from 2 to 5, not from 5 to 2. Similarly, for the next one, we're going from 3 to 6. We are not including the 3, x is greater than 3, but we are including the 6, x is less than or equal to 6. So round brackets around the 3, square brackets around the 6. For the next one, x is between -1 and 4, not including the -1 and not including the 4, so round brackets around both of them. For d, x is smaller than or equal to 2, so it's all the values from 2 all the way to the far left, or in other words, from negative infinity up to and including the 2. Negative infinity, that's not a number, so we're not including it, but the 2 is a number and it is being included, so square brackets around that. Last one, x is greater than 3. So in other words, we're talking about all the values from 3 to the far right, from 3 to positive infinity. We're not including infinity, it's not a number, and we're not including 3 either. X is strictly greater than 3. So this is a sort of notation that I'm expecting us to be able to use when we're describing solutions to inequalities. I may ask for your solutions in interval notation, and so this is the sort of answers that I'd be looking for if I were looking for answers that were in interval notation. And so sometimes we might have cases where it's not just one interval, but two intervals together. And the symbol that we use to connect two intervals or to combine two intervals together is this symbol, which we would read as a union. It looks sort of like a letter U. So something like this, all the values from far left up to 3 together with, or union with, all the values that are larger than 5. So if you were thinking in terms of a number line, if I wanted to talk about what are the values that we're looking at here, these would be all the values that are everything to the left of 3, as well as all of the values that are to the right of 5. Those would be the values that we'd be talking about when I mention that interval negative infinity up to 3 union everything larger than 5. So for this inequality in this example, I have all the values between -2 and 1, including the -2. And I've also got all the values which are larger than or equal to 4. So if I were writing this in interval notation, again, we're always going to go from left to right, from smaller value to larger. So I have all the values from -2 to 1, including the -2, not including the 1, together with, or, all the values which are 4 or larger. So everything from 4 to the far right. And so we're including the 4, so square brackets, round bracket around the infinity, because of course that's not a number, so it can't be included. Some properties for inequalities. There's a lot of things on this page, and a lot of it is similar to the same sort of statements that you could make about equations, that you could add a same amount to both sides of an inequality just like you can to an equation. You can subtract a constant amount from both sides just as you could with an equation. There's a couple of places where things work a little bit differently with inequalities versus with equations. With equations, we can always multiply both sides by any number, positive or negative, and we can divide both sides by any number, either positive or negative, and left side would still be equal to the right side. For inequalities, there's a little bit of a plot twist here, which is statements 2 and 3. What happens depends on whether we're multiplying by or whether we're dividing by a positive number or a negative number. In 2, the number that we're multiplying by or dividing by happens to be positive. And if that's the case, then the inequality is in the same direction as it was to begin with. So if you start with a less than, it'll stay as a less than. On the other hand, if you were multiplying or dividing by some number that's negative, notice that that changes the direction of the inequality. That if you started off with a less than b and you multiplied both sides by a negative number, it would now change to a greater than. Or if you divided, it would also change to a greater than. Now there's a couple of other little properties to throw in the mix, and both of these are fairly straightforward, the fourth and the fifth one. The fourth is essentially telling us in words that if something happens to be negative, then its reciprocal will also be negative. Or if something happens to be positive, then its reciprocal will also be positive. And so not a big surprise there. I mean, if you're thinking about positive numbers, you flip them, they would stay positive. Think about a negative number, flip it, take the reciprocal, it stays negative. So number 4 is not really a surprise. Number 5, I'll use this sometimes as we're getting close to writing our final solutions out to an interval problem. Sometimes you may want to switch the order of the numbers. So if you didn't want to write a less than b and you wanted to switch who's on the left side and who's on the right side, that will change the direction of your inequality. That would change it into b greater than a. You have similar sorts of properties here. I just mentioned these properties for what if it's a less than. You have similar sort of properties for greater thans, for less than or equals to, and greater than or equal to. Basically, the big story here is if you are working with inequalities, the one thing you have to be especially careful about is multiplying or dividing the sides by a negative amount, because that will change the direction of your inequality. So there's one other little caution here, and this ties into the business of if you multiply by a negative, it changes the direction. So the caution here is multiplying by something involving a variable is kind of a problem, or dividing by something involving a variable is a problem, because if you don't know what the value of the variable is, then you don't know whether it's something positive or something negative that you're multiplying or dividing by, which means you don't know whether the inequality should change directions or not. So the big caution here is we really should never be multiplying or dividing inequalities by things involving variables unless we happen to know that the variable is positive or unless we happen to know that the variable is negative. But if we're thinking about trying to solve for a variable with an inequality, multiplying or dividing by things involving that variable is a terrible idea. We should avoid that as best as we can. There's always a better way to work around it. So I'm going to just solve a few inequalities here, and for all of these I'm expressing my answer in interval notation. So I won't just finish with x greater than some number, I'll also have to then state my answer in interval notation after I'm done. So working with this, for the most part, we treat it just as you would an equation. You can move things from one side to the other. So if I bring the 3 to the other side of the inequality, I have now 1 on the right side. And if I'm dividing both sides by 2, I'm dividing by a positive number. So that means my inequality won't change direction. That means I'd be left with x is greater than a half. So as far as my solutions go, these would be all the values which are greater than a half. Greater than, but not an equal to, so not including the half, and of course not including infinity, since that's not a number. One more. This I could start out with dividing both sides by -2, or I could start out with expanding the bracket on the left side. Either way, it would be fine. I'm going to expand. And again, the one thing here is it's only when we're multiplying both sides of the equation or multiplying both sides of the inequality or dividing both sides of the inequality by a negative that we switch direction. Just me expanding this, that's not multiplying both sides of the inequality by a negative, so I don't switch the direction of my inequality. However, when I get to this point here, after I've moved the 2 to the other side and I've now got -2x less than or equal to 5, if I want to divide both sides by -2, and I do, that will have the effect of switching the order of my inequality. Instead of being less than or equal to, it will now be greater than or equal to. So for my solutions, those would be all the values that are -5/2 and larger, or all the values from -5/2 and all the way to the far right, including the -5/2. It's greater than or equal to, but not including the infinity. So round bracket around the infinity. One more. So we're looking at this, and I've got a rational expression on the left-hand side here, 5 over 3x minus 2, and you might be tempted to try to clear out the denominator, but of course the denominator involves x, and we don't know if x is positive or negative, so we have no idea whether multiplying would require us to change the direction of the inequality or not. So I won't be multiplying both sides by 3x minus 2. That's not the way that I'll be going forward. But what I'll be noticing here is that I have an inequality that is greater than 0. So in other words, I have a rational expression that is greater than 0. That fraction is always positive. 5 over 3x minus 2 is positive. And if this is positive, then that means the reciprocal of it should also be positive. So that 3x minus 2 over 5 should be greater than 0. And now I could multiply both sides of this equation by 5. Multiplying by 5 is multiplying by a positive number. That won't change the direction of my inequality. On the left side, when I multiply by 5, it gets rid of the denominator. On the right side, when I multiply by 5, it stays as 0. So I've got 3x greater than 2, or that x is greater than 2/3. So my solution is all the values that are larger than 2/3. Everything from 2/3 to the far right, not including the 2/3. So round bracket around the 2/3. Okay, the last little bit to talk about would be compound inequalities, and these would be statements where we have more than one inequality. So something maybe like this: 3 less than -4x less than or equal to 9. That would be an example of a compound inequality. And so what we could do would be to just deal with the entire inequality, the entire compound inequality, as one whole item. So for example, I could divide each of these numbers by -4, which would make all of my inequalities change direction. Or if I wanted to, I could add 1 to each and every number that I have in my inequality. I could do anything that I normally would do with a regular old inequality with a compound inequality, just applying it to all parts. That's one option. The other option for solving a compound inequality is to split it into two separate inequalities. So if you were looking at this inequality, you could say, well, there's actually two inequalities there. 3 needs to be less than -4x, and -4x needs to be less than or equal to 9. You could just solve each of these separately, find out what are the solutions to both of them, and then whatever they have in common, since it has to satisfy both of them, the first inequality as well as the second inequality, well, those would be your solutions to the compound inequality. And we're going to work through a couple of examples. One way, treating it just as one single inequality, and then the other, splitting it into two. So for this inequality, I have a compound inequality, and the thing that I'm noticing here is that there's only one x in this entire thing that I've got going on, which means I will be able to isolate the x by itself. So that's my plan here. I'm going to isolate the x, which is in that middle term, and so what I'm going to do is I'm going to get rid of this denominator, this 5, by multiplying everybody by 5. And since I'm multiplying everybody by 5, that's multiplying by a positive number, the direction of my inequality won't change. So I'll still have a less than and a less than or equal to. So I've got now 5/4 less than 2 minus 3x less than or equal to 5/3. And now I want to, again, isolate the x, so I want to get rid of this 2, so I'll subtract 2 from every side of the inequality. 5/4 minus 2. In the middle one, when I subtract the 2, I'll just be left with -3x. And 5/3 minus 2. And now I'm just going to use my calculator to simplify that. 5/4 minus 2, that's -3/4. And 5/3 minus 2, that is -1/3. And then finally, to solve for x, I'm going to divide everybody by -3, and when I divide everybody by -3, that's going to change the direction of all of my inequalities. So -3/4, when I divide it by -3, I get 1/4. -3x, when I divide it by -3, I get x. -1/3, when I divide it by -3, I get 1/9. And my inequalities will change direction because I divided by a negative. So now I have x is 1/4 is greater than x, which is greater than or equal to 1/9. Now, before I write my solutions using interval notation, remember for interval notation, we always go from smaller number to larger number, or from left to right. And this is actually written with the larger number first and the smaller number last. So what I'm going to do is just rewrite the order of my inequality with the 9th first and the 1/4 last. So that means 1/9 is less than or equal to x, which is less than 1/4. Remember that if we decide to switch who's on the left side and who's on the right side of our inequalities, that the inequalities will switch their order along with them. So x being greater than or equal to 1/9 is the same thing as saying that 1/9 is less than or equal to x. Similarly, saying 1/4 is greater than x is the same thing as saying x is less than 1/4. So now I have everything. I can say that my solutions are the values between 1/9 and 1/4, including the 1/9, but not including the 1/4. So round brackets around the 1/4, square brackets around the 1/9. And one last example. With this one, I don't have just a single x. I have x's on all sides of my inequalities, and so I think trying to isolate x is maybe a little bit of a problem. So what I'm going to do instead is split this up into two separate inequalities. That 5x minus 2 is greater than 3x plus 1, and 3x plus 1 is greater than or equal to x minus 7. So I'll solve these inequalities separately, and then whatever the solutions are will be the values of x that satisfy both of those inequalities. So starting with on the left, I'm going to move the 3x to the other side, which leaves me with 2x. I'll move the 2 to the other side, which gives me 3. So I have that x needs to be greater than 3/2. I didn't switch the direction of the inequality because I divided by a positive number. And for the second one, I'll do the same sort of thing. I'll bring the x over to the left side. That gives me 2x. And I'll bring the 1 over to the other side. That gives me negative 8. I'll divide both sides by 2. And I have x must be greater than or equal to negative 4. Now, as far as what are the solutions, this is where I'll draw a number line to help me visualize what's going on. Here's negative 4, here's 1, here's 2. 3/2 is 1.5. So if we're thinking about x being greater than 3/2, we're talking about the values from 1.5 all the way to the right. And for negative 4, x being greater than or equal to that, we'd be talking about all the values from negative 4 all the way to the right. And so what are we looking for our solutions? We're looking for what do these two intervals have in common, and what they have in common are all the values that are larger than 3/2. This is why for this, the solution are just the values that are larger than 3/2. Because for this compound inequality, we need the left side to be true, and we also need the right side of it to be true as well. We need 5x minus 2 to be greater than 3x plus 1, and that happens when x is greater than 3/2. But we also need 3x plus 1 to be greater than or equal to x minus 7, and that happens when x is greater than or equal to negative 4. And so the solutions are when both of the inequalities are satisfied, or what they both have in common, and what they have in common are the values which are greater than 3/2. I want to also mention one other little bit of notation that I've kind of introduced here a little bit slyly, which is this negative 4 and the 3/2. You might notice that one of the dots I've colored in and the other one I haven't. This is something that we'll see later on with graphing, that if I have a hollow circle, this would be, for example, at the 3/2, this is to indicate not including the 3/2, or that there is no point at the 3/2 mark. On the other hand, the filled-in circle that I have for negative 4, that's a way of indicating that I am including that negative 4. Okay, so this brings us to the end of this video and also to the end of Chapter 2.